Wastewater, as the name suggests, is a byproduct of human activity, either directly as human waste or as a result of human activities both domestic and industrial. Wastewater may infiltrate the sewer system as groundwater infiltration and as stormwater that enters from roof drains, foundation drains, submerged manholes and runoff from rainfall and snowmelt. Domestic wastewater sources are categorized as greywater discharged from the kitchen, general washing and the bathroom. The foul water source is from the toilet, latrines and exhaust tracts. Industrial wastewater sources are majorly discharged from factories, e.g., manufacturing and chemical processes. Key facts about wastewater. Wastewater has chemical and physical characteristics. Domestic wastewater physical characteristics are: fresh aerobic domestic wastewater has been said to have the odor of kerosene or freshly turned earth. Aged, septic sewage is considerably more offensive to the olfactory nerves. The characteristic rotten egg odor of hydrogen sulfide and the mercaptans is indicative of septic sewage. Fresh sewage is typically gray in color. Septic sewage is black. Wastewater temperatures normally range between 10 degrees centigrade and 20 degrees centigrade. In general, the temperature of the wastewater will be higher than that of the water supply. This is because of the addition of warm water from households and heating within the plumbing system of the structures. 1 cubic meter of wastewater weighs approximately 1 ton. It will contain about 500 grams of solids. 1/2 of the solids will be dissolved solids such as calcium and sodium salts, as well as insoluble organic compounds. The remaining 250 grams will be insoluble. The insoluble fraction consists of about 125 grams of material that will settle out of the liquid fraction in 30 minutes under quiescent conditions. The remaining 125 grams will remain in suspension for a very long time. The result is that wastewater is highly turbid. Chemical characteristics of domestic wastewater. The number of chemical compounds found in wastewater is almost limitless. To describe these chemical properties, most often the consideration is limited to a few general classes of compounds. These classes often are better known by the name of the analytical procedure used to measure them than by what is included in the class. The biochemical oxygen demand (BOD5) test is a case in point. Another closely related test is the chemical oxygen demand (COD) test. Famous myths about wastewater. Myth number 1: resolving urban sanitation is all about toilets. In fact, providing access to a toilet, a latrine or a sewer connection is only part of the solution. The SDGs now require that human waste is conveyed, treated and reused, disposed of safely and sustainably. The full sanitation service chain needs to be sustainably managed. Myth number 2: domestic wastewater produces waste that is a nuisance to be eliminated. In fact, human waste contains valuable nutrients. These can be recovered and reused as soil conditioners or fertilizer. Energy can be produced from both heat recovery and biogas combustion. Water can be recycled for industrial, agricultural and even potable use. Such underutilized value, when monetized, can generate revenue to offset service costs. What might go wrong without an efficient wastewater system? Wastewater treatment protects a community's life and health. Where the sanitation standards are low, most often there are likelihood of prevalence of diseases and epidemics. Bacteria, viruses, and parasites, including worms and protozoans, are the types of pathogens in wastewater that are hazardous to humans. Fungi that can cause skin, eye, and respiratory infections also grow in sewage and sewage sludge. Scientists believe there may be hundreds of disease-causing organisms present in sewage and wastewater that have yet to be identified. The water sources might also be contaminated. The report, titled A Global Decline in the Microbiological Safety of Water, a Call for Action, estimates that, worldwide, 80% of infectious diseases may be water-related. Diarrheal diseases traced to contaminated water kill approximately 2 million children and cause about 900 million episodes of illness each year. Wastewater treatment consists of a combination of processes used in steps to remove, kill, or inactivate a large portion of the pollutants and disease-causing organisms in wastewater. The modern wastewater treatment process, sewage water both domestic and industrial, can be treated and reclaimed for reuse and discharged back into the natural water system. There are several steps involved in this treatment process as outlined as follows. Step 1: Screening and pumping. The incoming wastewater passes through screening equipment, where objects such as rags, wood fragments, plastics, and grease are removed. The material removed is washed and pressed and disposed of in a landfill. The screened wastewater is then pumped to the next step. Step 2: Grit removal. In this step, heavy but fine material such as sand and gravel is removed from the wastewater. This material is also disposed of in a landfill. Step 3. Primary settling. The material, which will settle, but at a slower rate than Step 2, is taken out using large circular tanks called clarifiers. The settled material, called primary sludge, is pumped off the bottom and the wastewater exits the tank from the top. Floating debris such as grease is skimmed off the top and sent with the settled material to digesters. In this step, chemicals are also added to remove phosphorus. Step 4. Aeration-activated sludge. In this step, the wastewater receives most of its treatment. Through biological degradation, the pollutants are consumed by microorganisms and transformed into cell tissue, water, and nitrogen. The biological activity occurring in this step is very similar to what occurs at the bottom of lakes and rivers, but in these areas, the degradation takes years to accomplish. Step 5. Secondary settling. Large circular tanks called secondary clarifiers to allow the treated wastewater to separate from the organic sediment from the aeration tanks at this step, yielding an affluent, which is now over 90% treated. The biology, activated sludge, is continuously pumped from the bottom of the clarifiers and returned to the aeration tanks in Step 4. Step 6. Filtration. The clarified effluent is polished in this step by filtering through 10-micron polyester media. The material captured on the surface of the disc filters is periodically backwashed and returned to the head of the plant for treatment. Step 7. Disinfection chlorination. To assure the treated wastewater is virtually free of bacteria, ultraviolet disinfection is used after the filtration step. The ultraviolet treatment process kills the remaining bacteria to levels within the discharge permit. Step 8. Oxygen uptake, water analysis and testing and final disposal. The treated water, now in a very stabilized high-quality state, is aerated if necessary to bring the dissolved oxygen up to permit level. Testing is done for proper pH level, ammonia, nitrates, phosphates, dissolved oxygen, and residual chlorine levels to conform to the plants. After this step, the treated water passes through the effluent outfall, where it joins the natural water flow system. The water discharge to the river must meet stringent requirements set by the Environmental Protection Agency, EPA, and the Clean Water Act. Pollutant removal is maintained at 98% or greater.
Before you leave, our team will be very happy if you can give this video a thumbs up. Remember to subscribe and click the notification bell so that you can be notified every time we upload a new video. Thank you for watching, and see you in the next video.